So here we have an example where we want to sketch y equals arctan of e to the x. So I'm going to follow the same steps. I'm going to get a very different looking picture. So let's see, my domain here, well, I know that e to the x has a domain of all real numbers. So I want to think a little bit about the arctangent function. So arctangent is something that has a range that's between negative pi over 2 and pi over 2 and looks something like this. But its domain's all real numbers. So whatever I output for e to the x will be fine to evaluate an arctangent. So my domain is all real numbers. In terms of asymptotes, if I look for y of 0, I have arctan of e to the 0, which equals arctan of 1. And we know the angle that has a tangent of 1 that's in the restricted domain is pi fourths. Okay, so we have this y-intercept of y of 0 equals pi fourths is one of our points. Are there any x-intercepts for this graph? Well, is there anywhere where tan inverse of e to the x equals 0? So if we look at doing tangent of both sides of this, we'd have e to the x equals tangent of 0, which would mean e to the x is 0, but there's no solution to that because e to the x is always greater than 0. So we have no x-intercepts for this particular graph. Okay, so let's see, what should we look for next? We probably want to look at whether there's any asymptotes for this particular graph. So let's take a look at the limit as x goes to infinity of arctangent of e to the x. So I think we might have seen this limit in a previous section, and now we're going to see how it's used to find asymptotes. As x goes to infinity, e to the x is going to infinity. And I see from my graph of just arctangent, as my what's inside here is going to infinity, I'm approaching pi halves. So my horizontal asymptote for this graph is y equals pi halves, at least as x goes to positive infinity. But what about as x goes to negative infinity? I'm going to be looking at arctangent again of e to the x. Well, as x goes to negative infinity, e to the x is going to 0. Remember that e to the x looks like this. So as I approach negative infinity, e to the x is going to 0. So looking at my graph of arctangent, if I'm approaching 0, then arctangent is approaching, 0. So I get 0 here. So I have a second horizontal asymptote of y equals 0. Okay, so now I need to start considering some derivative information. So I've got these asymptotes. There aren't going to be any vertical asymptotes since we don't have anywhere where the function is not defined. Okay, so what about some derivative information? Well, the first derivative here excuse me, is going to be involve us using the chain rule. So we're going to have 1 over 1 plus e to the x squared times e to the x. So we have e to the x over 1 plus e to the 2x. And we have to determine where that's equal to 0. But that would be where the numerator is 0, but e to the x is never 0. So y prime equals 0 for no x values. Okay, so in terms of our sign chart, we're going to have the same sign for all values that we can plug in. And if we look at y prime here, any x value that I plug in is going to give me something positive, which tells me that my function is always increasing. And I have no local extreme values. Okay, so what about the second derivative? Well, we found the first derivative was e to the x all over 1 plus e to the 2x. So our second derivative is going to involve using the quotient rule. So we're going to have our bottom function here times the top function minus the top function times the derivative of the bottom function all over that bottom function squared. So this simplifies a little bit. So we've got e to the x plus e to the 3x minus 2e to the 3x all over 1 plus e to the 2x squared, which gives us e to the x minus e to the 3x all over 1 plus e to the 2x squared. So I'm trying to determine where that's equal to 0. So I'm looking for where this numerator of e to the x minus e to the 3x is 0. So if I factor out an e to the x, I have e to the x times 1 minus e to the 2x is 0. E to the x equals 0 has no solution. Okay, so I just need to look for where 1 minus e to the 2x is 0. So then I'm looking at using natural log. So natural log of 1 equals 2x. Natural log of 1 is 0. So I have x equals 0 is my only critical point here. So I look at making my sign chart here for my second derivative. So I put 0 on there. And then I see what's happening, what my sign is here on either side of 0. So if I plug in something a little bit smaller than 0, like negative 1, I'm going to have e to the negative 1 minus e to the negative 3, so that's 1 over e minus 1 over e cubed. So 1 over e cubed is going to be smaller than 1 over e, so I'm going to get something that's positive here. But then if I plug in something a little bit bigger than 0, like 1, I'm going to have something like e minus e cubed. And e cubed is going to be bigger than e, so then I'm going to get something that's negative. So y must be concave up and then concave down. Okay, so we need to put this together into a sketch for our graph. Okay, so what was some of the key information? Well, we had horizontal asymptotes at y equals pi halves and y equals 0. We had a y-intercept at 0 comma pi fourths. We had no x-intercepts, which makes sense with our horizontal asymptote, although we know it's possible to cross a horizontal asymptote away from the ends of the x-axis. But we do have no x-intercept. We know that we're always increasing. And we know that y is going to change from being concave up to being concave down on either side of 0. Okay, so first thing to do would be to plot those horizontal asymptotes. So I have y equals pi halves and y equals negative pi halves. And I can also plot this y-intercept of 0 pi fourths. And I know I'm going to be concave up until I get to, let's see, this y-intercept is also my inflection point. So I'm going to be concave up until I get to, whoops, I drew our horizontal asymptote in the wrong place. I was thinking about our tangent function. Here our horizontal asymptote is y equals 0, not y equals negative pi over 2. So sometimes we have an asymptote that goes over one of our axes, so we have y equals 0 here. And then I'm going to need to be concave up and then concave down. So we get something that looks like this. So it looks kind of like the arctan function, but in a little bit of a different location. So now let's look at how we can compute these slant asymptotes, which is another kind of limiting behavior that a function can have. So if the limit as x goes to infinity of our function minus a line is equal to 0, where m here, the slope of the line, is not 0. Of course, if the slope of the line is 0, we're talking about a horizontal asymptote. If the slope of the line is non-zero, then we're talking about the graph having a slant asymptote. And for rational functions, which is what we're usually going to be looking at to determine slant asymptotes will occur when the degree of the numerator is 1 more than the degree of the denominator, so that we can rewrite our function as some line plus some rational function here that is going to 0, so that in the limit we're approaching this line mx plus b. This is also equivalent to talking about the limit of the difference between the function and the line mx plus b going to 0. And the way we'll try to find equations of slant asymptotes is by using long division or polynomial long division. So if I look at something like this, where I have 2x cubed plus x squared plus x plus 3 all over x squared plus 2x, to rewrite this as a sort of equation of a line plus some remainder term, I'm going to be looking at 2x cubed plus x squared plus x plus 3 divided by x squared plus 2x. And then I think about how many times does x squared go into 2x cubed. In other words, what would I have to multiply x squared by to get 2x cubed? And here the answer would be 2x. So I write that above x. When we're doing this polynomial long division, we can think about each one of these powers of x as sort of being a placeholder, as in regular division. So I'll put that 2x over the x. So then I'll multiply 2x times x squared plus 2x, which is going to give me 2x cubed plus 4x squared. And then just like in regular long division, I'm going to subtract that. So I've got x squared minus 4x squared. So I'm going to have a negative 3x squared here. Then I bring down x, and I see how many times does this go in. So let's see, I would have negative 3. So I'd do negative 3 times this, so I'd have negative 3x squared minus 6x, subtract again. So I've got x minus a negative 6x, so that's like x plus 6x. So I have 7x, and then I bring down the 3, and that's my remainder term. So I've been able to rewrite this function here as 2x minus 3 plus 7x plus 3 all over x squared plus 2x. So that's my remainder term. Since this term is going to 0 as x goes to infinity, this is my slant asymptote. So my slant asymptote is y equals 2x minus 3. Okay, so now we want to take this idea with slant asymptotes and combine it with a curve sketching example. Okay, so I've got y equals x cubed plus 4 all over x squared. So this is a little bit less complicated one than the previous one. And I want to go through the different steps and come up with a sketch of the graph of this function. So looking at this function, I can see that it's defined everywhere except at 0. So the domain is from negative infinity to 0, union 0 to infinity. So there is no y-intercept. In terms of x-intercepts, an x-intercept would occur where that numerator is equal to 0. So if I solve that, I get that x would have to be the cube root of negative 4, which would be the same thing as negative 1 times the cube root of 4. So I have this x-intercept as one of my points. Okay, so let's look at some asymptotes of this function. So what about vertical asymptotes? Well, there is a point where the function is not defined. It's not defined at 0. So we could look at what's happening to this function as x goes to 0. So I could look at the limit as x goes to 0 of x cubed plus 4 over x squared. And it may help in this case to rewrite this. We're essentially using long division here, but it's a little bit easier than before. I can break this up into x cubed over x squared plus 4 over x squared and see that what I have is x plus 4 over x squared. So as x goes to 0, let's see, this second term here is going to be going to positive infinity because I'm going to have 4 over a small positive number plus 0. So I'm going to get positive infinity out of this. Okay. So what about whether there are any horizontal asymptotes? Well, horizontal asymptotes, I would be studying what's happening as x goes to infinity. So again, I can look at it of this simplified form. And as x goes to infinity, that's going to turn out to be infinity because 4 over x squared is going to 0, x is going to infinity, so there's no horizontal asymptote that way. And similarly, if I look at the limit as x goes to negative infinity, I'm going to get negative infinity. So we have no horizontal asymptotes, but this does tell us at least what the function is going to as I approach those two different extremes. So what about slant asymptotes? So I've already shown that we can write this function as x plus 4 over x squared. So let's just go back and remember that to check that we are dealing with a slant asymptote according to this definition here, I'd have to show that the limit as x goes to infinity of my function minus the equation of my slant asymptote is equal to 0. So it looks like y equals x is going to be my slant asymptote. But to check it, I'd need to look at the limit as x goes to infinity of my function, which is x plus 4 over x squared minus the equation of my slant asymptote. So I see that those x's would cancel, and 4 over x squared would be going to 0 as x goes to infinity. So it is a slant asymptote. Okay, so we've done the asymptote information, the domain, and the intercepts. So let's go ahead and look at finding some derivatives of this. So remember, this is x plus 4 over x squared. Our first derivative is 1 plus, now it probably helps to write this with our negative exponent. So we have 1 plus negative 8 x to the negative 3. So we have 1 minus 8 over excuse me, x cubed. So we want to see where that's 0. So y prime equals 0. So that will be 0 when 1 is equal to 8 over x cubed, or when x cubed is equal to 8, which occurs when x is equal to 2. So remember, our domain was all x except 0. So when I'm making a sign chart, I gotta mark 0 on there because something could change on either side of that. And then I've also got 2. So looking at what my derivative is when x is smaller than 0, like negative 1, I'm going to be looking at 1 minus 8 over a negative 1, so that's like 1 plus 8, so I'll get something positive. If I plug in something like 1, I'm going to have 1 minus 8, so I'm going to get something negative. We plug in something bigger than 2, like 3, I'd have 1 minus 8 over 27, so that's going to be, give me something positive. So my f is going to be increasing, then decreasing, and then increasing, so I have a local min at 2, comma, let's see, what do I get if I plug 2 into this? Well, 2 squared is 4, so this will be 1, so I'll have 2 plus 1. So I have a local min of 2, 3. I don't have a local max, although it looks like I might have something at 0, but remember the function's not defined at 0, so we have no local max. So what about the second derivative? Well, I'm going to need to look at where the second derivative is 0, but first I need to know what the second derivative is. So let's see. This is 1 minus 8x to the negative 3. So I've got 24x to the negative 4, or 24 over x to the 4th. So that's always going to be positive. So the only thing I need to put on my sign chart for my second derivative, I guess I switched from using f's to y's here. So I'm going to have to look at what's going on either side of 0, but on both sides my function y is positive. So it's concave up on both sides of that place where the function is not defined. Okay, so we need to put this information all together and sketch a graph. Remember our asymptote information, we've got a vertical asymptote at x equals 0, we have no horizontal asymptotes, and we have a slant asymptote at y equals x. So we can draw y equals x here. That's y equals x. I've got this vertical asymptote at x equals 0, so I'll draw that. I also had found earlier that, let's see, I had negative the cube root of 4, comma 0 was an x-intercept. Okay, so I can go ahead and sort of estimate where that is, somewhere around here. Okay. Remember that my function was concave up the whole time on either side of 0. Okay, and just to remind ourselves about the increasing and decreasing behavior, my function was increasing, then decreasing, then increasing. Okay, so let's see. I've got to approach this. I've got to be increasing and concave up until 0. So increasing and concave up and approaching these different asymptotes. So I start out with something that looks like this, and then on the other side of 0, I'm still concave up, I'm decreasing and then increasing. Oh, I also had a local min. My local min was occurring at 2, 3. So 2, 2 would occur on the line. So 2, 3 is a little above the line. So somewhere around there I've got my local min. and I've got to be approaching these asymptotes. So I've got to do something like this and then go and approach this line. So there's my asymptotes and the sketch of my graph where I've got this point down here is my local min. Okay. So we're going to do some more practice with these different curve sketching problems on Wednesday next week. And we're also going to start talking about combining this with using the calculator. So in section 4.6, we're going to talk about graphing with calculus and calculators, try to combine these different ideas to get the most accurate graph that we can. Have a good break, everyone, and I'll see you next week.